In this section of Chapter 3, we're going to be specifically talking about our bond characteristics. So the different types of characteristics that we can have based on the type of bond that we have, single, double, or triple, and the types of overlaps of those orbitals. So one thing that we're going to see is that we are going to have free rotation around single bonds, but we're not going to have any rotation around our double and our triple bonds. And this is due to the type and the amount of overlaps that we're going to see within our orbitals. So for our single bonds, I'm specifically going to look at a carbon-carbon single bond. And that carbon-carbon single bond is going to come from our sp3 hybridized orbitals. So each one of my carbon atom has its four sp3 hybridized orbitals. So remember, that's what accounts for our tetrahedral electron domain geometry. So two of those orbitals are in the plane of the paper. One is pointing out at you, and one is going back behind the screen. The second carbon atom will have the same exact type of sp3 hybridization, where one of the orbitals is coming out at you, one is going back behind the plane, and two of them are in the plane of the paper. You'll see that we do have the overlap between two of those hybridized orbitals, and it's a nice sigma symmetry where we see the overlap on the internuclear axis between our two carbon atoms. This is our single bond that we will have between our two carbon atoms. With this single bond, we are going to have freedom of rotation around that single bond, meaning that the relationship between the three other sp3 hybridized orbitals on one carbon can change their relationship with the other three sp3 hybridized carbon atoms on the other carbon atom. So we can see that relationship in three-dimensional space change as we have freedom of rotation around that single bond. When we start having our multiple bonds, our double and our triple bonds, we no longer have this freedom of rotation within the structure itself. So I'm going to look at a double bond between carbon atoms. So I'm going to look at an sp2 hybridized carbon atoms. My sp2 hybridized carbon is going to come with one sp2 hybridized in between the two atoms. I'm going to put this in the plane of the floor. So you can kind of think of one of those sp2 hybridized orbitals pointing out at you, one going back behind the screen. I'm going to do the same thing on my other carbon atom, putting it in the same plane so it's parallel to the floor for those sp2 hybridized carbon atoms. Those sp2 hybridized carbon atoms in the plane of the paper are going to overlap. So again, this is our sigma symmetry. We see an overlap of those hybrid orbitals in between our two nuclei. But remember, with our sp2 hybridization, we also have that unhybridized p orbital on each one of these carbon atoms. So I'm going to show that unhybridized p orbital, and I'm going to put this one in the y-axis. So since I already have things on the z-axis and the x-axis, these p orbitals are going to end up on the y-axis. So when we get ready to form that double bond, or the second sharing of electrons within the double bond, is due to the pi symmetry, or the overlap of those p orbitals. So because those overlap is above and below the internuclear axis, we lose our freedom of rotation. So we no longer have freedom of rotation here. Because if I start to rotate one of those carbon atoms, like we did in our single bond, I lose the overlap of those p orbitals. So if that p orbital starts to go anywhere but in that y-axis, it is no longer overlapped with the other one. So we lose our freedom of rotation, which means the relationship between the other two sp2 hybridized orbitals remains constant. It is not allowed to change in their three-dimensional space as that molecule is there. It is a set spatial arrangement, unlike when we have our single bonds, where we can have some freedom of rotation in how the three-dimensional relationship between all the other bonds. Because we lose our freedom of rotation within double bonds, we do have two configurations that you do want to be familiar with, and we saw this in an example from our problem set in the last chapter. So if I have my carbon-carbon double bond, and we looked at having our chlorine atoms being either on the same side or on opposite sides, I cannot get through this through freedom of rotation. These are very different structures for us. Remember, one of them was going to be polar, one of them was going to be nonpolar. When I have the two chlorine atoms on the same side, I would denote this with the term of cis. So I would denote this with the term of cis. That cis tells me that those two hydrogens are on the same side and the two chlorines are on the opposite side, but still on the same side. When I have my two hydrogens on opposite side and my two chlorines on opposite side, we refer to this as being trans. So this would be what we would refer to as a trans relationship between our structures, our attachments to that double bond. We will include this type of information in the name. When we get ready to name these structures, we will include that information in the name. When we look at these, they will have some different properties. Remember, we said the cis configuration is nicely polar, while the trans configuration was nonpolar. So we will see some different physical properties based on the spatial arrangement of our atoms around the double bond. We do need to be very, very careful when we define cis and trans. We are really defining that hydrogen relationship, whether the hydrogens are on the same side or on opposite sides of that double bond. So if we have structures that one of the carbon atoms contains two hydrogens, this would not have any cis or trans relationship. Because the one carbon atom has two of the same attachments, it has two hydrogens on it, so we would not be able to classify this as cis or trans. We would see the same thing if I had two chlorine atoms, but they were both on the same carbon, and both of my hydrogen atoms are on the same carbon. Both of these would not have any cis or trans relationship. Again, because my hydrogens, no matter how I flip them, they're going to be identical with how their relationship looks around that double bond. So do be very careful when we define cis and trans. We're specifically looking at those hydrogen atoms. And if our two hydrogen atoms are on the same side of the double bond, we would refer to that as being a cis relationship. If we have our two hydrogens on opposite sides of the double bond, we will refer to that as being our trans relationship. If we only have one other attachment, so notice we had three hydrogens around the double bond, there's no cis or trans relationship. If both hydrogens are on the same carbon atom, there's no cis or trans relationship. Oftentimes this term of cis and trans is italicized in the name, which is why I have it underlined here on the notes, because I cannot italicize on the screen. So oftentimes when we get ready to start naming these structures, we will name them and they will be italicized for us. So let's talk about how some of this information is going to influence some of our bond characteristics. So the type of hybridization that we're going to have, whether that's sp3, sp2, or sp, it is going to impact our bond length. If we impact bond length, it also impacts bond strength. So remember, the shorter the bond, the stronger the bond. So if we change our bond lengths, we will change our bond strength. So hybridization will influence both of those. Hybridization is also going to influence what we refer to as the effective electronegativity. The effective electronegativity is going to be the tendency of an atom to hold the electrons in a bond due to the type of hybridization that it has. So our effective electronegativity is the tendency of an atom to hold on to those electrons due to the type of bond that we have. So let's kind of look at some examples with this in terms of what we're going to be seeing. So if I'm going to start, let's start with our sp3 hybridization. So again, remember we have that nice tetrahedral nature, so we're going to have some bonds pointing out at you. We're going to have some bonds going back behind the screen of the paper. We'll then compare that to sp2 hybridized structures. So this would account for our double bond between our carbon atoms. And then we'll also compare that to our sp3 hybridized carbon atoms, which would have that triple bond between our structures. So if we talk about our carbon-carbon bond length, what we're going to see is that our single bonds, that sp3 hybridization, is going to be longer. This one is about 154 picometers. The double bond will be about 134. picometers. And no, I do not expect for you to memorize these values. I'm just going to give them for you for a comparison, but you do need to know the relationship. So our bond length is going to increase for sp3 hybridization, and it will be the shortest for our sp hybridization. Which means if we talk about our carbon-carbon strength, it is exactly the opposite. The stronger bond will be the sp hybridized, the weaker bond will be the sp3 hybridized. Because of that hybridization, we're also going to see some deviations in the carbon-hydrogen bond lengths. So we will see some deviations in the carbon-hydrogen bond lengths as well. In our sp3 hybridized atom, it's about 108 picometers. Notice there is a difference between the carbon-carbon bond length and the carbon-hydrogen bond length. Hydrogen is smaller of an atom, so the bond distance, the bond length, is also going to be smaller compared to that of a carbon-carbon. If we look at our sp2 hybridized, this is about 107 picometers. And if we look at it with our sp hybridization, this is about 105 picometers. You'll notice that we still see the same trend. The longest bond will be the sp3 hybridized bond. The shortest will be the sp hybridized bond. Hopefully you were also observant and noticed that the change was not as drastic with the carbon-hydrogen bond as we saw with the carbon-carbon bond. This is because hydrogen is never hybridized. It is always the same. The only part that is changing for the bond is the carbon. So we don't see as drastic of a change because we're only impacting one atom. The carbon-hydrogen bond strength still has the same relationship. The strongest bond will be the sp hybridized bond. The weakest bond would be coming from the sp3 hybridized carbon atoms. All of this relationship is due to the amount of S characteristic that we see in each type of the hybridized bond. So remember, each hybridized bond, the percentage that we had that represented the S characteristic, that spherical characteristic, increased as we went from the sp3 over to the sp because we had less and less p characteristic associated with it. So it's really due to the amount of S characteristic that we see, that spherical characteristic. When we talk about our effective electronegativity, so when we talk about that effective electronegativity, we are going to see an increase from sp3 to sp2 to sp. sp will have the highest effective electronegativity, while that sp3 will have a lower effective electronegativity. So again, this is really defining for us the more electron density will be on the carbon atom in an sp hybridized bond than what there would be in an sp3 hybridized carbon atom. So pulling some of that electron density away from hydrogen. So it's an effective electronegativity based on the type of hybridization. It's not going to impact electronegativity, polarity, as much as what we saw with electronegativity from our last chapter, but we will see some slight deviations in that sharing of electron. They will not be shared completely the same between our sp3, sp2, and sp hybrid orbitals. We see more of an attraction with sp hybrid orbitals than we will with the sp3 hybrid orbitals.